Hello friends, welcome to another tutorial in network analysis and synthesis. In this series we are doing AC analysis of circuits, and in this tutorial we'll talk about a technique, node transformation matrix or nodal analysis for AC circuits. Now this technique is similar to nodal analysis in DC circuits, but it has a few tricks that I'm going to mention in this video. So if this is something that interests you, then please keep watching. Node voltage analysis or node transformation matrix formation of AC networks is identical to that of DC networks, but we need to generate a matrix in this format. So what we'll do is we'll format a matrix out of admittance multiplied by voltage, giving us the current. And I'll illustrate that with an example. For example, we have this network where there are two sources and both of these are current sources. Now there's a key point here. There's a quick tip. If you have voltage sources in the network, you are advised to convert those voltage sources to current sources by the source transformation method. And if you wish to learn source transformation where you can convert a voltage source into current source or current source into voltage source, you could refer my video in the playlist for that. But if you have all the current sources in the network, then it becomes a lot easier to form this matrix that we are targeting. Okay, so what happens is in this network I've chosen 3 nodes A, B and C, and I've chosen voltage V1, V2 and V3 at nodes A, B and C respectively. Because of the presence of the current sources, it becomes now very easy to identify one current at these nodes. For example, if you look at node A, I1 is entering, and there must be some current flowing through Z1 that can be represented as voltage V1 upon Z1, and some current flowing through Z2 can be represented as V1 minus V2 upon Z2. Now this process is similar to that we used in DC analysis. Now this Z could be anything. This could be a combination of R and L, could be a combination of R and C, etc. So you need to figure that out. This could be 2 plus 5i if it's a resistance and inductor combination, and this could be 2 minus 3i if it's a resistance and capacitance combination. Okay, once we have this current equation at node A, so one current is entering, two are leaving, so we have this equation, and from this equation we segregate the coefficients of V1 and V2. That's the next key point. So segregating coefficients of V1 and V2 and equating them to I1 will eventually take me here at closer to this formation. And the next key point is that 1 by Z1 can be represented as Y1 because reciprocal of impedance is admittance, and 1 by Z2 can be represented as Y2. So finally I've gotten this equation in where we have Vy on the left hand side and current on the right hand side. Similarly at node B we have this current entering, and I assume all the other currents to be leaving, and this is by the way leaving for sure. So what I get is V1 minus V2 upon Z2, the current here, and then I2 is on the other side because it's leaving. V2 upon Z3 is leaving. V2 minus V3 upon Z4 is also leaving. And again we need to isolate the coefficients of V1 and V2 and V3s, and the coefficients of V1, V2 and V3s are going to be in terms of Z's. So reciprocal of that will be Y's. And so I get minus V1 into Y2, V2 into Y2 plus Y3 plus Y4, and minus V3 into Y4 is equal to minus I2. And at node C, I can see that this I2 current is entering and two of the currents are leaving, two are entering. V2 minus V3 upon Z4 is also entering, I2 is also entering. This current is leaving, which is flowing through Z5, and this current is also leaving, which is flowing through Z6. So I have two things on the right hand side and two things on the left hand side. Again, separating the coefficients of V's, V2 and V3, I get this equation. So this equation is also V into Y is equal to I. So I name this equation as 2, I name this equation as 3. From 1, 2 and 3 I can get a matrix, and that matrix is known as node transformation matrix. So the coefficients of V1 are put in the column 1 here, coefficients of V2 are put in the column 2 here, coefficients of V3 are put in the column 3 here, and then multiplied by V1, V2 and V3, which are needed to be found. And on the right hand side, I1, I2 are known to us. And now that was the quick tip, because we want all the sources to be current sources and they must be known to us. And from this, from the matrix method, we can calculate the values of V1, V2 and V3. So that is how quickly we can solve AC networks also using node transformation matrix method, or nodal analysis for short. And I hope this quick tutorial on nodal analysis for AC circuits was of help. If you liked the video, give it a thumbs up, consider subscribing, share this video, comment for any suggestions and any other videos that you want me to make. Until then, take good care of your health, and I'll see you around in the next video. Bye bye.